just before this one. I had one person in class and about 5 in Zoom. So we're doing pretty good, I'd say.
I'm going to the gym for spring break, Saturday, let's go. I started doing FPV drills. They're fun. They're expensive though, like stupid expensive for what they are. But like it's like a roller coaster without going on. So I think that I have a private model. Oh yeah. It cost me like $500, but it goes to 360 hertz. What are you doing at 360? Don't worry about it. Like you play Minecraft at 360? What's up? Play Minecraft? You put the 6 feet up to all the way down. That's something that people feel scary. It's terrifying.
Well, welcome back, folks. Looks like we can get started. So we had a big exam. We should probably talk about that. Exam 2, the grading for that one is going to be the second class I grade for. I had just one class before this one. So I'm going to start on Friday grading by starting with your homework assignments. I'm going to work from the late ones up to all the way to the current due ones to 11.1, I think is the last one they'll make it on there. Then after all that's graded, I'll grade your exam 2 and that'll give you a really good idea of where you're at in the course. If you like, you can check your course grade as this changes. For every assignment I grade, I update your overall course grade for the entire class. So it's going to change bit by bit. And when it comes to computing for the grade on exam 2, it'll be based off this table as before. Homework is massively impactful in this class. And now 70% of the course is the average of exams 1 and 2, since that's just all the information we have for the exam side. So that's all be computing your course grade. Any questions about the exam, folks, so far? Okay, once exams are graded, I'll post some basic summary stats down below here, just like on exam 1. And just like on exam 1, you'll be able to find the solutions as well if you want to check them out later on. So that takes us to where we're currently at, section 11.2. This is kind of weird because we did section 11.2 on, I think, Wednesday. Then we did a review day on the 13th, and then we did an exam day. So feels like it's been a while. Let's refresh a bit what we did with section 11.2, and then we'll move to the problems. But any questions at the moment, folks? Okay, also should mention that although we do have class tomorrow, I'll be here. I understand that if it's a hard one to make because spring break is next week, but we'll have class tomorrow. And even on spring break, there's no classes or office hours and that kind of stuff. But if you're working on math, if you have any questions, don't hesitate to email. I'll always be checking my email, definitely first thing in the morning. Just doesn't feel like the day starting out right if I don't. So if I see your questions there, I'll make that my first part of the day to get to all of your questions. And it can be a lot of questions. I'm a pretty fast typist, so it does not annoy me at all. But I think that's all of my announcements. Let's jump back to what we were doing in section 11.2. We left here, but again, it's been a while, so let's kind of recall what we're doing, since that's not easy to say right away for these kind of problems. Let's go to the very top even. Just as a reminder of what we're doing in this section, we started with the sequence in section 11.1. And the sequence was just a listing out of terms. We used methods which were really carried over for Calculus 1 to find the limit of the sequence. If the limit exists, we said it converged. And if it didn't, we said it diverged. But the sequence just lists out all the terms. A related sequence starts summing the terms. S1 is just A1. S2 is the sum of the first 2 terms, and so on. This one right here is the sum of the first n terms, so we call it Sn. And it's the associated sequence of partial sums. That sequence is really, really important to us because if we're going to define a series, it's defined in this way. That's the sequence of partial sums right here. This is the total series because it has the dot, dot, dot. It's saying n equals 1 from infinity. But now we're defining what we even meant by adding infinitely many terms. It means take the first terms, add them up, but then take the limit of the number of terms you're adding. That's just the limit of the sequence of partial sums once again. And if that converges to a finite number, we call it the total sum of the series over here. And that's what we checked out down below on the telescoping sum. This is a weird and specific kind of series where if you expand out the nth partial sum, which is nothing but a1 plus a2 all the way to an, you get tons of cancellations, leaving just 1 minus 1 over n plus 1. Add up all of those together just means taking the limit, and that limit came out to exactly 1. So now what we're saying is, if you keep on adding stuff and put a plus here and a dot, 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 that's the series. It's not Sn, it's the entire thing right here. And the sum of all that, we call it exactly 1. Any questions about that idea so far? Okay, so in short, a series is taking the sequence and putting pluses where you see the commas. But then at the same time, it's looking at this and taking the limit. If the limit exists, that's the value of adding up all the terms in the sequence. And we looked at how to do it for the telescoping sum. That's kind of a one-off in this class. But the one that isn't a one-off is the geometric series. If you take A, then multiply it by our so-called common ratio R, then multiply it again on the third term and again on the fourth term and so on, we have a geometric series. And this geometric series, well, it sometimes converges. When it converges, it's because the common ratio R is less than 1 in absolute value. The total sum on this comes just A divided by 1 minus R. And that's all we have to do for the geometric series test. Write out your series in this kind of format so we can see what R is. Less than 1 implies convergence, and this is a formula for that convergence. Extremely rare to have a formula like that. And if it's greater than or equal to 1, we have divergence. We just call the whole thing the geometric series test. So we applied it a couple times. Part A was kind of annoying because we had to come up with a formula for an. But once we got here, that's the common ratio R, negative 5 halves. It is greater than 1 in absolute value. So we said this whole thing diverges. It just gets bigger and bigger. Well, larger positive sometimes, larger negative the other times, because it's also alternating at the same time. It's like it's diverging in the worst possible way. Some points go upwards, some values go downwards. But let's do it all over again. Here's the problem of the day. Any questions at all, folks, running through those methods? Okay, so for this one right here, a couple things we want to take a look into are, does the indexing really start at 1? If it doesn't, we need to re-index it. We'll show how those methods work on part C coming up next. After that, we need to try to find the common ratio R itself. Let me blow that up just a little bit. We can see what it is from this, but here's another way to work. Let's give this a new name and just call it summation AN. It's just kind of like putting down a placeholder, like saying x equals or f of x equals. I'd even put in the n equals 1 to infinity. Kind of weird. It's a major shorthand now, but if you prefer, you can put it in if you like. If you left them off, it's just a way to name this as a shorthand. But also what I've done is I've named what AN is. AN is thought of as the nth term of the series, but you can also think of it as the nth term of the sequence as well. It's equal to e power 2n divided by 10 power of n. And what we want right now is, let me circle that in a better way, common ratio R to power n minus 1. So we need to correct the exponent and we need to get it in one spot. One step with exponent work is where the red dot is, we can call that e squared n divided by 10 power of n, and that gets us started. Now, if we have the same exponents, we can re-express this under a common base. The base is e squared over 10, all raised to power n. Next part we're going for, and I think this is kind of hard to read actually. Let me get a different screenshot on that. I took 2 screenshots on it and it just got a little bit worse in quality with each screenshot. There we go. I think it's a little bit easier to see. We have the common ratio R now. We need to express it to a power n minus 1. So this is our next step right here. That's pretty fast, right? You just take this whole thing, factor out e squared over 10, leaves behind e squared over 10 to a power 1 less. n minus one. So this is everything that we want to get started in the geometric series. We have r, it's raised to the right power. We need to determine convergence or divergence right here. Looks kind of funny though, e squared over 10. A couple things you might do is just write out what e is, which would then mean e squared is approximately, really roughly, approximately 9. And that tells you, yeah, this is not exactly 9/10, it's approximately 9/10, but it's definitely less than 1. Or instead of doing some weird estimate methods, you could just throw it all into a calculator. E squared over 10 gives us 0.73. So we're looking at convergence. Let's say here, r, e squared over 10, it's less than 1 in absolute value, but you don't need to put in the absolute value sign if you're looking at something positive. This is the condition for convergence, so we can say converges by the geo series test. But we're not done. Now that we know it converges, the follow-up question is, what does it converge to? So that's going to be our last line to follow up with this. Any questions first, folks? Just determining whether it converged at all. Okay, well, let's pick up over here. You can either use the shortcut, summation an, or use the full structure right over here to write out the next step. Just to show how this shortcut might work, let me write out this way. Summation an with the decorations going from 1 to infinity, which are optional. This is just a way to name the original series, is now going to be a summation as we go from 1 to infinity of e squared over 10 divided by, multiplied by e squared over 10 to the power n minus 1. So that's the r in the formula over here. We carefully factored out that and collected it because it's the a in the formula coming down over here. All we have to do is just write it in. It converges, and the total sum of infinitely many terms added together is e squared over 10. Let me fix that 10 there. Divided by 1 minus e squared over 10. It's kind of a weird looking structure. We do want to simplify this. And fastest way to simplify these things in the geometric series is just look to the denominator. We have a least common denominator of 10, so just go times 10 over 10, and we get e squared divided by 10 minus e squared. So we did it, folks. We analyzed the format of the series. We determined its geometric series and wrote out this step right here, but we're in the section where we're doing geometric series, so it wasn't a hard determination. But once we got convergence, we used the second half of the formula right here to say what it converges to. So kind of a weird process. This is infinitely many terms, and if you implement this in, say, like Excel, you're computing finitely many terms. But the more you push Excel, the closer it's going to get to that exact figure. This is where the summation is heading towards, in other words. Well, let's try it out again in part C. Any questions first, running through this full method? Okay, so here's where it gets a little bit messed up at this point. This one has a lot going on. The powers are off. There's stuff in the numerator, denominator, there's an extra factor, but even more offensively, the indexing is off. Starting at 0 is actually not good for us if we're using a formula that specifically says indexing starts at 1. So we need to be really, really careful with this one. Actually, let's leave this theorem screenshot just right in this spot. And before we even take on part C, let's just discuss a little bit about reindexing. If you have a sequence that goes summation n equals, let's say 0 to match up our case, 0 to infinity, and you can reindex this in any way you like. You can make where the red dot is, just go up or down. And some problems we do want to index down because when we're dealing with power series, Taylor series, Maclaurin series, indexing starts at 0. But Here, if we're using that formula, indexing starts at 1. You could say that down over here, we want to change the index, go up 1 here. But if you increase by 1, then over here, this will be a to power n minus 1, decrease by 1 here. So we just balance it. Whatever we did over here, we reindex everywhere n occurs and do the opposite thing. So if I went up 10, this would be an minus 10. If I went down to negative 10, that's weird, but absolutely allowed. This would be an plus 10. So whatever action you take, just undo that action over here. In fact, what it means is the geometric series itself could be reindexed. You could take that whole thing and say summation n goes from 1 to infinity, a to the power r, n minus 1 is just as good as a summation from 0 to infinity. But I went down on that one. Anyone see what should go right over here then? Let me think about that. Wouldn't be a minus 2 on this one. It'd be an n, yeah. If we go down 1 here, this is now an n plus 1 minus 1. So just a power n altogether. So it's kind of weird, right? It means you don't have to reindex that one. But I think it's still a good idea in this problem because when you go to use a geometric series, the formula is given to you like this, as our author does. Probably not the best idea to reindex it, right? Just good to know you can if you wanted to. So what I'm going to do is reindex the problem so it matches the formula. Let's start by saying this is a summation as we go from n equals 1 to infinity of, well, I increased by 1. So now we do the opposite thing, decrease by 1. That's 3n minus 1 plus 1, so it's 3 power n. Below it's 4 times negative 6 power n minus 1. And you know that's a good start because if the problem looks like this, I'm going to undo this in just a moment. If the problem started off like this, that's actually a harder question than what we're doing on the right because the powers are even more off and now the indexing is correct. We would just have to do exponent work on this as it stands. But because the index started at 0, we reindex it to 1. The exponent work here is just not as bad. In fact, let's take a different approach of what we did over here. We worked on the nth term, took a whole bunch of steps because there was a good amount. Here, there's not a lot of steps to take. Let's just work with the series directly in this format. It's now sum from 1 to infinity. We can factor out 3 from this numerator to leave 3 by 3n minus 1 over 4 times negative 6 power n minus 1. Now we have the same powers. We can bring this under 1 base, 3 divided by negative 6. So sum from 1 to infinity, 3/4 times 3 over negative 6 to the common power n minus 1. We should reduce that, but we could determine convergence divergence right here if we wanted to. Let's do it in one extra line. We have a summation from 1 to infinity of 3/4 multiplying the reduced value, negative 1/2, power n minus 1. And at this point, we have the common ratio r. In absolute value, it really is less than 1. We need to say it on paper, though, so let's write down absolute value of r is 1/2, less than 1. On each one of these series, we need a conclusion of either convergence or divergence. But convergence happens right here. So we can now say converges by geoseries test. Last thing we need to do is just say what it converges to. We've got the right structure, the indexing correct. We have the value a, we have the common ratio r. It's just a matter of shoving it back into this formula right here. So here's what the last steps look like. We go 3/4 divided by 1 minus -1/2. And then because it's a complex fraction, the easy way out on this is take the least common denominator, which is going to be 4 on this problem, multiply by 4/4, and in the numerator, it's just a 3. Denominator is going to be 4 plus 2. So that's a 3/6. Comes out exactly as 1/2. Weird coincidence. It comes out as the absolute value of the common ratio r. That is a pretty striking coincidence on this problem. But that means we've got it, folks. The summation of this infinitely many terms, or this one when we re-indexed, it has the same exact meaning, is a complicated way to write 1/2. Kind of weird to see that just from how it started. Any questions at all, folks, on that last test there? Okay, well, that's dealing with the geometric series. And as a reminder, notice how the details that we've been putting down on essentially every series problem, except the telescoping one that we were dealing with. We always put down the information that either told us it converged, or we put the information that told us it diverges when it was greater than 1. We gave the conclusion, convergence or divergence, and then we mentioned the test. This is what was going to be kind of a routine process when we go to do these problems, kind of captured in the statement. Really starting on these exercises, the homework set, because now they're mixed. For each test of convergence divergence used, we want to state the name of the test. And it could be really brief. You might just say geoseries like that. It could be really, really brief. If you said by geoseries test, I would know what you meant. That's a well understood acronym. Just make sure your acronym doesn't involve multiple tests, then it's ambiguous. But you have to say something that indicates what test you used. If you just said geoseries, that's fine as well. That's just a shorthand of saying you use the geoseries test, is how I would take that. And there's a real purpose to all of this. This is helpful for partial credit. That way, if you analyze the series wrong, but your steps were right for the misanalysis, I could give partial credit if I knew which test you're actually using. But really the larger thing about all this is the geometric series test isn't even the only test in this section. We're going to get another powerful test. And then 11.3, we pick up 2 more. We just keep on getting more and more tests under our belt. There's one document that I want to move down. Let's move this down. And so the point to all of this is that this thing contains all of them, and we must learn them all. Best way to get all this information in your head is to say what you used the moment you used it. So when we use a test for divergence, we'll just say by the test for divergence, or the geometric series test, or the p-series test, and so on. And by doing that, you're going to really learn this well. You'll keep it really separate in your mind, which one is which. And notice the danger in this document. For example, geometric series has convergence at r greater than or equal to 1. And that's the format, right? Compared to this format, that's a p-series, and convergence is at greater than 1. That's the reason of just saying this on paper, saying it in your mind. You have to tell them apart because they look really similar. We're studying them by making those statements each and every time. So, oh, hang on. Let me convey this correctly. Convergence is over here. I didn't even highlight the right part. That's divergence. So notice how it feels like they're going in opposite directions. What we're trying to tell apart, is it a geometric or is it a p-series? This one is in section 11.3. So we'll get into a habit of doing that. It's kind of annoying. If you didn't put that down on paper on a homework problem, you'll lose a point. Not a big deal. But it's mainly so that we're prepared for that when we do them as exam problems as well. If this is a 10-point exam question, you could lose a couple points by not saying what test it is, actually. But what we're going for now is this test. It's a ridiculously powerful test when it works. And it is, in the world of sequences and series, the most misapplied test at the same exact time. we often want to say we have convergence when the limit is zero, but it's not true. This test for divergence only goes in one direction, and it only gives one conclusion, divergence and only divergence. But it also comes from a different place. It really starts right here. If the series is convergent, then the limit is zero. That's a powerful statement, and let's think about it. What is this right here? If we say we're dealing with a series and it converges, it means summation as n goes from 1 to infinity, an equals a1 plus a2 plus a3 plus a4 plus, it goes on forever. It's equal to the limit as n goes to infinity of Sn. There's a lot of ways to say this. You can rewrite that this means it's the limit as n goes to infinity. The n going to infinity is captured with the dot, dot, dot to say infinitely many terms. Limit as n goes to infinity of a1 plus a2 plus a3 plus a4 plus an. On the structure here, it's indexed by the limit as n goes to infinity, so it just grows and grows and grows. And we're saying in every one of these statements, it's equal to, let me see if I can shorten this up just a bit, equals some value, let's call it L, because it really truly arises out of a limit. This L is a real number, it's finite, it can't be infinity or negative infinity. And what we're saying is, as we add more and more terms inside that bracket, the sum doesn't blow up, it's contained, it's approaching something, maybe it's pi or zero or a half, something like that, whatever that limit happens to be. But then we think about what does that mean for the actual terms of the sequence? That's what this is all about. If we keep on adding infinitely many more terms, the nth term of the sequence can't converge to, say, 5. Because if the limit of an is 5, you're eventually adding 5 infinitely many times. That does blow up. That goes to infinity. The limit has to be 0 itself. That's the key insight of theorem 6. Conversion of a series always implies the limit itself for the sequence converges, and it converges to 0 in fact. So kind of a wild statement. This is convergence of the series. But what we're talking about here is totally different. This is convergence. And not just convergence, it's convergence specifically to 0 of the sequence an indexed from 1 to infinity, which is a1, comma, a2, comma, a3, and so on, infinitely many terms there. So converges to 0 of the sequence if the series itself converges. So that's the gist of theorem 6. It's a powerful theorem, but it's not exactly the theorem you'd want to use, right? Because the question in this chapter is, does the series converge? Yeah, go ahead.
So, is the limit of infinity is a sequence, right?
Over here, yes.
So will those not be common instead of pluses, or am I just?
Right over here?
Yeah.
Yeah, these would be commas right here, as opposed to pluses.
Oh, I'm talking about like the A1, A2.
Over here,
On the right, yeah.
yeah, this stuff over here is now talking about the series
Oh.
itself. Absolutely. It's kind of hard to kind of separate them in the mind. Also, this is really compactified as well. But yeah, all this stuff here is now the series itself. Even over here, we're talking about the series. But it's saying that the an and the limit, now it's talking about the sequence. Those terms are getting closer and closer to 0 as they're comma separated. It's weird having to deal with two abstract objects at the same time, or more, one is extra abstract. But does that help out to see what's going on with that one? Awesome. So before we finalize theorem 6, think about what it's saying. It's saying essentially this. Oh, geez, hang on. There's got to be a way to carry that down. There we go. It's essentially saying if P P is the statement that the series is convergent. Then, which we use arrow to say, convey if then, so the arrow is the then. Let me try a better symbol there. P, not the reals. I don't know why I put the real number system there. Actual P implies Q. So that's how the statement works. This statement is true as it stands, but Q implies P is the converse. And it is false, unfortunately. If we start with the assumption that the limit is zero, we don't have the conclusion that the series converges. And that's a really unfortunate fact. That's something we'll take a look into on the very next problem. But any questions about it so far? Okay, the main takeaway here is if you have an if-then statement, the logic goes one direction. It's like a train track and you cannot reverse this. If you could reverse this, we would visualize it this way and we would say it's convergent if and only if the limit is zero. But sadly in mathematics, it's just not a true statement. It only goes one way. Another way to think about this is if you have a sequence an is 1 over n, that's the harmonic sequence, it goes to zero in the limit. But we've discussed the harmonic sequence as a series, sum all the terms, it in fact diverges. That's a counterexample showing why this is actually false. We can't reverse the logic. But that's okay. Something else is true. The thing that is true from the implication statement here is the contrapositive. The contrapositive is a statement that goes like this. It's an attempt to reverse the arrows of logic. But if you do that, it goes this way really. Not Q implies not P. So if the limit of an is not zero, or if it just doesn't exist outright, then this doesn't converge, it diverges. That's the way we can make a conclusion on the series, even though the theorem itself is a conclusion on the sequence. We want conclusions on series in this section. So it's a little bit unfortunate of a theorem, but that's what's going on with theorem 6. We don't use it a lot, and we'll explain why in a moment. But example 4 is a way to use it at least once now that we're dealing with it. So recall the statement of the theorem. It says a convergent series implies a convergent sequence, and even more, it has to converge exactly to zero and nothing else. So here's a weird series. It says it is known that the series is convergent. So you'll have to trust me on this for the moment. But we can test that when we're in the comparison tests later on, sections 11.4. But knowing that this is convergent, we can take a look at the sequence itself, test it for convergence and divergence. But up here it says if the series converges, then the sequence, an, if we put the limit as it goes to infinity, it's just automatically zero. So this is like the world's fastest problem for a sequence. We can say by theorem 6, limit as n goes to infinity of an, which is the limit as n goes to infinity, cosine squared n, 1 plus n squared, is automatically zero, and we don't have to think too much about it. Honestly, though, if we did think about it and we didn't use theorem 6, we might have resorted to a common tactic to say the denominator grows without bound, just gets bigger and bigger. The numerator is a cosine function, so it does vary, but this is varying between 0 and positive 1. So this is something finite, bounded rather, divided by something that grows to infinity. In the limit, it has to be 0 at this point. But theorem 6 is also a nice clean argument as to why. Now, with theorem 6 on the table, like I mentioned, we don't use it a lot, but in spirit we do. It's logically equivalent to the contrapositive, and the contrapositive, we write out that statement in full, is called the test for divergence. Other textbooks have a very common name for this, so if you've seen information, if you study from different sources, this is also called the nth term test. I think that's actually the more famous name than the test for divergence our author uses. So that's a good one to keep in the back of your mind if it just pops up at some point. Test for divergence says, if the limit does not exist, or if the limit is non-zero, then the series is divergent. This is a full-on contrapositive to theorem 6. But same issue with theorem 6, it's an if-then statement, which means we cannot reverse the logic on this one either. If we start with, say, that the series is divergent, we can't move backwards and say the limit does not exist or is non-zero. That's kind of unfortunate. And here's another big problem. Even if the limit is 0 on this, it doesn't mean convergent over here either. It's really very restrictive on how this test works. And divergence is the only conclusion. Really just duplicating what the conjugate is saying right up above here. So because it's the most misapplied theorem potentially in chapter 11, we're going to take another look at what's going on right here. Theorem 6 is the easiest theorem to apply incorrectly in chapter 11. Hang on, because the converse is false, state the converse of theorem 6. Hang on, that's not quite what I wanted to say. Let me strike this through. I really want to stick to my guns here that theorem 7 is the easiest one to misapply. Let me rewrite this as theorem 7. Theorem 7 is the easiest theorem to misapply. The converse is false. And we'll state the converse of theorem 7. Sorry, I'm not too sure what went on my notes. I need to correct this later on. Let me do a really fast reminder. Correct lecture notes 11.2 on example. I didn't put an example number on there, did I? I guess that's example 5. Okay, I'm going to have this fixed here, and I'll have it fixed on the blank lecture notes as well, so there isn't some lingering weirdness. The other thing I want to eliminate was this. I'm really trying to talk about theorem 7 specifically, not bring theorem 6 back. We're done with it. So I guess I struck it through and deleted it. It's gone now. So let's focus on the nth term test, the so-called test for divergence. It's the easiest theorem to apply incorrectly. Okay, now I believe that statement. This one is the one we're talking about. The converse is false, and we're going to state the converse regardless, just to see what it looks like. The converse to this statement would say, start right here. If the series is divergent, excuse me, let me change that around. Yeah, divergent is what I wanted. Then we would read out this part of the statement. Limit as n goes to infinity of an does not exist, or limit as n goes to infinity is not equal to 0. Don't quite like that or. Let's say an end on there just to make it feel logically correct as possible. That would be what the converse of this theorem would look like. And we're saying down below that it's automatically false. We should have a counterexample that we could exhibit. So what could be our counterexample? Let's take a look into this one. The harmonic series. We've looked into this one before, and it's in section 11.3. We're actually going to show ourselves that it diverges. Our author shows this as an example in 11.2 in a different method. But the harmonic series is a summation as n goes from 1 to infinity of 1 over n, and it diverges. We've only looked into numerical evidence again ourselves, so we're going to have to cite our authors for the proof until we're in that section. So the converse of this theorem, if we write out the conclusion going backwards, would say divergence means a limit does not exist and it's not zero at the same time. But we know that's not the case. We can say next, however, limit as n goes to infinity of 1 over n, we know that to be 0. That was our first sequence problem in section 11.1, which means the sequence converges. And not only that, it converges to 0 as well. So this whole statement is false. We try to read the logic backwards to say if something is divergent, then limit does not exist and is not 0. It's totally false. This is the counterexample. This does diverge, and yet the limit is 0, conflicting with what this statement says entirely. So this is a really tough problem in a certain sense. And theorem 6 also has issues. Theorem 6, if we look into it, would be if the harmonic series converges, then the limit over here would converge to 0. That's a big problem as well. Let's take another look at that theorem just one more time. Theorem says, if the series converges, then the limit is 0. If you find the limit 0 right here, it's really tempting to say we have convergence over here, but that's also not true. Again, the logic only goes one way. It's like a train track, and you have big problems when you try to reverse it. Sometimes the reversal is true, but not in these cases. Starting with the limit equaling 0 does not give us convergence whatsoever, unfortunately. But that's, again, one of the reasons why we have loads of tools. Test for divergence is at the very top, because if I give you a random series, this is a good one to look into just to see if it applies. If it doesn't, determine if it's a geometric series, and if it's not, think of it as a p-series. If it's not any of those, then we start getting a little bit more fancy. This is where it gets a little bit convoluted in the middle of chapter 11. But by the time we get to ratio and root tests, it starts to become a lot less bad. Integral test is at the bottom because it's the test of essentially last resort. It takes the most steps, and it's not as widely applicable as you think it is, because you have to compute this integral, which means you also need an antiderivative, which could be fantastically hard out of nowhere. So that's where all this is going. Putting it all together, here's the test so far. We have a geometric series test. We have the test for divergence, or the nth term test. And this is just a related fact about combinations of sequences. If you have a linear combination where it's a constant multiple, or a sum, or subtraction, you can break these up. The reason this works is every one of these is defined through a limit, really. And you just use the constant multiple rule from calculus 1 on those limits, which says the constant can come out, or that the limit of a sum is the sum of the limits. And so we're just carrying over all of those limit statements. That is correct. Yeah, if we multiply our terms of the sequence together, these formulas would break down. Yeah. Other questions so far? Okay, so these instructions down here are pretty much the same instructions that I've been writing in on the homework down below. The reason I'm being so specific with these is it's also the assumption for what you'll do to solve the problems on the homework setting. So we'll practice hitting all these bullet points on homework. If you miss any one of those, I'll alert you and say you forgot to say if it converged, or you forgot to name the test, or you forgot to show the condition of the test. It won't be anything too major. But we'll check that we hit each one of these on every one of these problems. Starting off with this one right here. My first question for you is it a geometric series that we're looking at down here? I agree with the class. This doesn't look quite like a geometric at all, right? Common features of the geometric series is n is an exponent. Here it's a base, so it cannot be geometric whatsoever. So that alone tells us geometric series is out off the table. Test for divergence is the next one. But if you look at that really closely, just this part, that's a rational function, right? Anyone see what the horizontal asymptote should be of that function? Good call. That means the limit is not zero, it's -1 immediately. We can just see it by visual inspection. That means we're looking at a divergence series automatically just by eyeballing it. That's kind of nice. But we've got to go through the motions. Here's what it looks like. We have to say the name of the test. I need to know that you know what the test is, and it also helps me apply partial credit as well. If you misapply the test, but you're doing the right things for that test, that's how I could apply partial credit. We could just say it right here. Test for divergence. If you're a fan of acronyms, you can say TFD, test for divergence, and that would always make sense. In the test for divergence, we can't just say diverges and moves on. We have to show, let's see, all necessary steps of the chosen test, but it isn't really much. We just take a limit, see what happens to the limit. We're in this case, it will exist, but it's not zero. So this is showing the actual steps of the test. Actually, let's color code this just a little bit. We stated the name for the test right here. Showing all necessary steps of the test looks like this. Limit n goes to infinity of an becomes limit n goes to infinity of 3n minus n cubed plus 4. And just to highlight what we've got going on here, it's a rational function with tie in the degree, numerator and denominator. So we just pull out the coefficients, -1 divided by +1. Or just -1. Showing all steps of the chosen test means we also have to say not equal 0. I would be picky if you didn't say that part, but it's a good thing to really say because what you're connecting is in your mind. That's a reminder it's divergence, and that's the condition you were trying to hit. So if you do say that, it's a pretty great reminder. We just need a conclusion now, and we can say either the series diverges. If you just said diverges, I'm okay with that as well. But sometimes we're looking into multiple things at once. It might not be a bad idea to say what diverges. So I'll say it on the notes just to be specific. So there's just no meaning to this as a series. The trouble is, as we take on more and more terms, those terms get closer and closer to just subtracting by 1 each and every time. This is all together negative infinity. Well, that's where the limit would be heading to. So we have diverges on this one, and that's all you have to do for these kind of tests. They're really fast, right? But kind of some of the difficulty is we have to identify test for a divergence applied in the first place. It's not so hard right now. There's only like 2 tests at the moment and just a related fact. But it gets tough when we're in this landscape, looking at all the tests simultaneously. And that's what this tedious steps are all about. Naming the test is making that connection in your mind when you say it each and every time. And saying what the conclusion is, showing those steps, well, you just have to do that on the exam as well. So this is reinforcing all of those steps. Now let's try it out again. Just like before, we want to determine what does this look most similar to. Let's grab some of this stuff from above. If we tried the test for divergence, it's a great test, right? The limit's fast, but it fails essentially all the time. If you took the limit of this as you go to infinity, my claim is the limit is 0. You know what? Let's do that right here, because this is a pretty good experience of actually solving a problem like this one. Test for divergence doesn't work. We're actually using the geometric series test in Theorem 8. But let's give it a try regardless, using test for divergence, just to see what goes wrong. Let's call this attempt 1. Test for divergence. So, sorry, say again? Integral test would be a good one on that, yeah. That would be pretty interesting to navigate through. So for test for divergence, we take limit, n goes to infinity, 4 plus 2 power of n divided by 3 to the power of n. The way we do this limit, we really major reason why we're doing attempt 1 is not just to show what goes wrong. It's important to know what goes wrong. It's also to see how to do the limit if it went right. If this was a reciprocal, the test for divergence would have worked. The limit would have been infinity and we're done. So we need to see what goes wrong here by taking the limit. The idea is the same with how you would do the limit over here on this one. If you didn't use a shortcut of analyzing and observing its irrational function, so that's its asymptote, you would have gone to the denominator, divide every term above and below by the most impactful term, n cubed. Here, the most impactful term is 3 power n. That's the only term in the denominator. So that's how we start. Limit as n goes to infinity of 4 divided by 3 power of n plus, when we divide this by 3 power of n, we get 2/3 to power n. We could just consolidate it as one common base, in other words. Dividing this by 3 power of n just gives us a 1, so nothing going on in the numerator. And then what about the rest of the limit? This part goes to 0 because we have a common ratio that's less than 1. As n gets larger and larger, this just goes to 0 right away. How about this part? Hang on. That goes to 0 as well. This is not what I was expecting here. Yeah, this actually works. Or excuse me, this actually fails. That's what I was thinking. Excuse me. I think I got just mixed up in my logic on this one. The limit comes out as a 0 because it's 0 both here and here. And I said this actually works, but that doesn't mean we have a conclusion, right? It means test for divergence. We often say it fails. That's a weird thing to say. It's not that the test fails, that the theorem is wrong, that it was proved incorrectly. What we mean is it fails in the sense it never applied in the very first place. Just because we got a limit of 0, it's different from this, doesn't mean we have a conclusion of convergence, because the logic doesn't go that way. We can't just change what's here and change the conclusion on this side. And if we try to use theorem 6, this one that says if the limit is 0, then you have convergence, that's a big problem too, because the logic goes only one way, to the right. You had to start with the convergence series and then conclude the limit 0. It can't actually go backwards tragically. So there's lots going on with this one. And you know, if this ever happens in an exam setting, if you ran out of time and just left this problem like this, it is partial credit. You did attack it. You found out that test for divergence doesn't apply. It's not a full solution, but it is good information. So now here is attempt 2. Any questions at all, folks, with why the test for divergence gives us no conclusion? Okay, now in attempt 2, we're going to try to analyze it as a geometric series, but there's extra problems with the numerator. There's really 2 terms here. So we're going to use theorem 8 to break it up as well. When we go to break it up, if we find any part is divergent, then we do have a big problem, but looks like we're going to be okay. There's 4 over 3 power of n. 2 over n over 3 power of n should give us the right thing. This kind of breakup we're doing only works if there's one term in the denominator. So this doesn't apply if it was the reciprocal, but we can say summation an, as n goes from 1 to infinity, is now a summation as n goes from 1 to infinity of summation an is referring to this whole thing. And now we take our first algebraic step and write 4 over 3 power of n plus 2 power of n over 3 power of n. Both of those look like they converge. And that's actually really important. You can't use this formula at all unless you had information of convergence here and here at the same exact time. If one of them diverges, but you're looking at the sum like this, the sum could converge because maybe something cancels out that allows for convergence. So it doesn't go backwards either. It's kind of a restrictive formula. But we are looking at 2 things that converge as a geometric series. So the formula does apply. This is going to turn into summation from 1 to infinity of this term, and let's fix this while we're at it. It's 4 times 1 over 3 power n is a way to re-express this with exponent laws. This collapses to 1 power of n divided by 3 power of n, and then you can multiply them together to get the fraction back. And then go plus summation 1 to infinity of 2/3 to the power of n. Again, they look like they're both convergent, so theorem 8 really does apply. We're going to show that, though. We're going to prove that it converges through the geometric series. If you use theorem 8, you don't have to state it. It'll just be clear that you did because of what happened in the algebra. Now for geometric series, we need to make sure index is right and the power on the common ratio is right. We have a problem here and here, so we need to drop the powers. Re-indexing doesn't help because we wouldn't start at 0. So on the next step, we can say this is equal to summation from 1 to infinity of 4/3 times 1 over 3 power n minus 1. So I factored out a third, multiplied against the 4. Now we have the 4/3. Plus on the next one, this one's a little bit easier to see. You just pull off 1 factor of 2/3. Leaves behind 2/3 power n minus 1. So now on both cases, we have a common ratio r. It'll go there. And we have the value a that goes in the numerator. But we still have to say how we're testing these. These are both geometric series tests. So we can say geo series test. Again, if you like acronyms, GST is totally fine as well. For the geometric series test, we have on this one, r equals 1/3, less than 1, so convergence. And then on this one, same thing. However, r is 2/3, less than 1, so convergence again. That means if they both converge, we can find their total sum. So this will turn into, it's kind of hard to carry down from here. You wouldn't want to recopy that whole thing, right? So if you want to write this down cleanly as possible, start with the shortcut symbol. Summation n goes from 1 to infinity, an equals to, and then we'll just carry this directly down so we can have some kind of parallelism, seeing everything in a column. We're using this formula down below twice. So on the first run, we go 4/3, divide by 1 minus 1/3, give it a little bit of space, and then do it all over again. On this one, take the 2/3, or excuse me, the 2/3. These fractions are all starting to look the same to me. Then 1 minus the other 2/3. And that's the formula worked out twice. We still need to simplify it, but we can simplify by multiplying 3 over 3 on both of those fractions. So next line, we have that this is a summation from 1 to infinity of an, just naming the original series. First one is going to be 4 over 3 minus 1. Second one after cancellation is 2 over 3 minus 2. So this one is 4 halves. So 2 on that, plus 3 ones, another 2. And altogether then it's a 4. So this weird thing, as n gets larger and larger, you're adding more and more terms, is approaching 4 at each new step. Kind of a weird one. It's weird to have to break things down in this kind of way, but occasionally that trick that we used going from here to here is a big trick, not just in this section. It can sometimes be applied in surprising ways. The sections 11.3, 11.4, 11.5. But the fundamental thing that made this trick work was the denominator had 1 term, allowed us to divide in this nice way. There's no long division, in other words. If it was a reciprocal, that whole trick is off the table, and this thing would diverge by test for divergence. What we did, folks, that's a pretty complicated one, just because there's so much stuff going on. That's just a lot to analyze at once, especially when we broke it down. This one's complicated because it's not so much stuff this time. It's because it just looks abstract. When you look at this one, what kind of a series does it look like to you all? Is this a geometric series, or is this one where we have to use tests for divergence? It all depends on cosine 74. Let's take a look at it. If it was the right cosine, maybe it's cosine 0, test for divergence will work on this, because cosine 0 to any power n whatsoever is only going to give you 1 each and every single time. And so that would mean you're adding ones infinitely many times altogether, automatic divergence by test for divergence. But if it's cosine 74, this is 74 in radians, it's something different, 0.08. So now if we took the limit of that, it would go to a 0. Test for divergence wouldn't work on it. Good call. It just doesn't look like it, right? It just feels too abstract with a cosine function thrown in, but it's truly geometric. The only thing that dictates that is n is an exponent. So this alone right here means it's a geometric series test. Yeah, that's a great call on that. I would say that's something that should work almost always. There are a couple exceptions. Those exceptions might be things like summation n goes from 1 to infinity. Let me think about it. It would be something that starts off looking good. Maybe it's e to the n. It's a geometric series at this point, but then we go like over n cubed. Oh. So that's like the only time there's a break on the pattern. If n's only role is an exponent, you're looking at geometric. So we have a geometric series test. That means we can say and rewrite this as summation from 1 to infinity. It's cosine power, or cosine of 74 to power of n, but we need to drop it to power n minus 1. So we do the normal thing. It just looks weird. Factor out one factor of cosine 74 from that whole structure to leave behind cosine 74, power n minus 1. So we now have the R value. And we already checked it out in Desmos. Cosine 74 is about a 0.08. So a critical thing is it's less than 1 in absolute value. We have convergence. So let's go here and say R, cosine 74, approximately a 0.08 altogether. The less than 1 is talking about that part. And because we have less than 1, we can include this part and say converges. We already named the test we're using, and this is the work of the test. You just have to say, what is the exponent? So I know that you know convergence was because that was not the exponent, the base, the common ratio R was less than 1. Then next thing you do is you take all of this stuff, drop it back into the geometric series structure right here, and you get an answer of cosine 74, 1 minus cosine 74 again. Weird problem, right? So that's how this one would end.
You got one of those. Oh, and
Oh yeah, so I have n at a weird value. Sorry about that. At power 1, I should be getting the 0.17 repeating. And just about any calculator, and same with math written in like a calculus class, if nothing is specified, the assumption is automatically, it's got to be radians. For degrees, it would have to be indicated this way, so we really knew what the right unit was. But any questions at all, folks, with this one here? Okay, this one's weird. It just feels abstract, but kind of takeaway with this problem is to try to force us to really see what makes a geometric series, analyze the role n is playing, and that makes all the difference. If it's an exponent, you're probably looking into geometric series. And we've got one more, but I don't know if we want to rush through this one in 2 minutes. This one's not too bad though. Think about what you would do to it. Any volunteers for what the test should be? Yeah, it's pretty much all we've got, right? Sorry, say again? Exactly. Then that limit is 2, right? That means we get natural log 2, not equal to 0. It's automatically a divergent one. But this will be a good one to refresh on when we come back on what our Thursday's class, I'd say. So Thursday's class, we'll finish this off, and then we'll extend to section 11.3, finally doing the integral test and the really nice p-series test. Already, p-series test is one that's really confusing when you check it against the geometric series. Take a look at what n is doing, and that's the best way to tell them apart. But this will be our stopping point for today. Have a great night, folks. If you have any questions, I'll be happy to help out. Otherwise, we'll just reconvene on Thursday and then go on a long dessert break. Take care, folks.
Have a good night.
Thanks, you too.
That's